Okay, so last time we met, we were talking about drawing molecular orbital diagrams for molecules, and the last example we did was CH2ClF. And we said generally our diagram is split into bonding, non-bonding, and anti-bonding sections, and then within each section, electronegativity tells us the order that they go in, with more electronegative atoms going toward the bottom, less electronegative toward the top. So one thing we haven't dealt with yet is pi bonding. So let's do an example with a pi bond, C2H4. So C2H4 involves pi bonding. So remember, if we were to draw what the sigma bond looks like between the two carbons, we have one carbon and the other carbon, and each one, in this case, is going to contribute what kind of orbital to the sigma bond? An sp2 orbital. So I'd have an sp2 orbital from this carbon and an sp2 orbital from the other carbon, and they'd overlap. What about the pi bond? What orbitals make the pi bond? All right, so it's going to be the p orbitals that make the pi bond. So there's one p orbital on one carbon atom. There's the other p orbital from the other carbon atom. Oops. All right, now remember what we said about bonding and anti-bonding orbitals. When we overlap two orbitals to make a bonding orbital, it's generally lower in energy than the original two orbitals that made it. When we make an anti-bonding orbital, it's generally higher in energy. The way we rationalized that was we said that in the bonding orbital, the electrons are closer to the two nuclei. In the anti-bonding orbital, they're farther away from at least one of the nuclei at any given time. So they get higher potential. When we think about the difference between a sigma and a pi bond, in a sigma bond, there's a lot more overlap, and the overlap occurs directly between the two nuclei. Okay? What that means is sigma bonding generally results in more stabilization of the bonding orbital. So the bonding orbital gets more stabilized from where it was originally. And the antibonding orbital gets a lot of destabilization compared to the atomic orbitals. With a pi bond, there's less overlap, so the energy difference isn't going to be as great. There's less stabilization from the atomic orbitals to the pi bonding orbital, and there's less destabilization from the atomic orbitals to the pi antibonding orbital. All right? So what that means is sigma bonding orbitals end up lower in energy than pi bonding orbitals, and sigma star orbitals end up higher in energy than pi star orbitals. Oops. So that's going to introduce an extra division into our into our MO diagram. Before we had it just split into bonding, non-bonding, and antibonding. Now we're going to say among the bonding, we'll split that into sigma bonding and pi bonding. And among the antibonding, we'll split it into pi star and then sigma star. So our general divisions now are going to be sigma bonding, pi bonding, non-bonding, pi star, and then sigma star. So among the sigma orbitals, we're going to, again, just arrange them by electronegativity. So I have CC and CH. I would put CC a little bit lower than sigma CH, and I've got 4 sigma CHs. Next up is going to be pi CC. We have no non-bonding orbitals in this molecule. We're going to have 1 pi star CC, 1 sigma star CC, and 4 sigma star CHs. So in general, those are going to be the divisions in any MO diagram we draw. Sigma, pi, non-bonding, pi star, sigma star. I would go and I would fill in my electrons. Now in my diagram I have 2, 4, 6, 8, 10, 12 valence electrons. So in my MO diagram I should have 2, 4, 6, 8, 10, 12 valence electrons. All my bonding orbitals are filled up. All my antibonding orbitals are empty. Question? Oh. So the question was, why did you mess up and draw your dotted line in the wrong spot? And there you go. No. Thank you. All right, so now we know basically all the principles we need to draw any MO diagram. And again, when I say to draw any MO diagram, I mean to draw a really simplified version of any MO diagram that's going to be good enough. So the summary is that in general, we have sigma, we have pi, we have non-bonding, pi star, and then sigma star. And that within each category, we split them based on electronegativity. And just to restate why it goes in this order, sigma bonding orbitals, they have the best overlap, so they have the most stabilization. Sigma star are at the top because they have the best overlap and the most destabilization. So it's like the best bad overlap, or the best destructive overlap. So that's the most destabilized. Question? So the question is, why does sigma bond have better overlap than pi bond? Well, you know, in these simple pictures I drew here, remember, sigma bonding orbitals are pointed straight at each other, so they overlap in a big area, there's a lot of space where they overlap. Whereas pi bonds, they kind of overlap just at the sides, and they only overlap a little bit compared to sigma bonds. Even though there's two areas of overlap, there's not as much overlap in either area, because they're not pointed directly at each other. And so when there's poor overlap, there's not going to be as much stabilization for making a bonding orbital. There's not going to be as much destabilization for making an antibonding orbital. All right, there's two more little subtleties that might come up. They're probably not going to affect any of the MO diagrams we draw directly, but there will be cases where we'll consider hybridization and formal charge as part of our distinguishing between two orbitals. So it's worthwhile to talk about the energy of different kinds of hybrid orbitals. All right, so let's think about our unhybridized orbitals. What kind of orbitals does every atom start with? An s and 3 p's. All right. How do they compare in energy? What's higher energy, the s orbital or the p orbital? P is higher in energy. Yeah. So we have s, and then somewhere higher in energy we have our 3p orbitals, which are equivalent to each other. All right. What about the hybrid orbitals? If I take an s and a p, if I take an s orbital and a p orbital and combine them to make an sp orbital, where do you think the energy of the sp orbital lies? Exactly halfway between. So my hybrid orbitals, I'll do in red here. An sp orbital would lie halfway between. All right. What about an sp2 orbital? We make that by combining an s with 2 p's. That would be a little higher. That would be 2/3 of the way up. Yeah. And then an sp3 orbital would actually be 3/4 of the way up. So the moral of the story is, it turns out, if you're looking at two carbon atoms with different hybridizations, an sp hybridized one effectively has lower energy orbitals than an sp2 hybridized one, which has lower energy orbitals than an sp3 hybridized one. So hybridization affects orbital energy. It's not something that we're going to include in our MO diagrams very frequently, but occasionally it becomes a useful concept. Yep. So the question is, does this continue when you have sp3 d orbitals? Well, it depends who you ask, because, you know, most professors I've worked with would contend that sp3 d orbitals are not a useful construct, because the energy of the d orbitals is actually much too high to actually contribute to bonding in any reasonable way. But regardless, sp3d would not be a hybridization we would ever use in organic chemistry. So, for instance, if we wanted to compare the sigma CH orbitals in these, we would probably say that the sigma CH orbitals from this ethane, which is on the far left, what kind of hybridization does the carbon have? So these sigma CH orbitals would be higher energy. Than, say, the sigma sp2H orbitals, and the SPH orbitals would be lower in energy. Oops. So hybridization is another factor that you will sometimes consider when thinking about the energy of molecular orbitals. And it turns out that has consequences that you'll learn about in Module 12. Where that molecule on the right, it's much easier to remove a hydrogen from that molecule. The one on the right. Yeah, because the CH antibonding orbital also would end up much lower in energy in that molecule. So the question is, so does hybridization affect both the bonding and the antibonding orbitals? And the answer is yes. Yep. You can, another way to think of this is you can think of an sp hybridized atom as more electronegative than an sp3 hybridized atom of the same element. So if you look at everything through the lens of electronegativity is a big concept for us. If you look at everything through that lens, one way to internalize this is to just think an sp hybridized carbon atom has effectively a higher electronegativity than an sp3 hybridized one. So the question is, are so I wouldn't think of the orbitals as being electronegative, but I would think you can think of the atom itself when it has a certain hybridization as being more electronegative when it has sp hybridization than when it has sp2 hybridization, and that's a little more electronegative than when it has sp3 hybridization. So the question is it because those orbitals are lower energy that the atom becomes more electronegative? I would say that's kind of a semantics question, or, like a chicken and egg question. Both electronegativity and orbitals, all of these are theoretical constructs that we come up with to rationalize. So I wouldn't say that one causes the other. They're all just ways that we approach thinking about the molecule. And so I just think it's helpful to me to have different ways to describe the same thing. Because, sometimes when one way fails me to think, a lot of times we refer to this as the amount of S character in the hybrid orbital. That terminology might escape me for a minute, but I might remember, but SP acts like it's more electronegative. So then I have having that separate description allows me to still use the same concept. All right, and then one more thing that's going to affect the energy of orbitals would be formal charge. We've seen this before. If you have an atom that has a positive formal charge, do electrons like it more or less because of its positive charge? If you're an electron, would you like an atom with a positive charge better or worse than a neutral atom? Better, yeah. Positive charge is going to be more attractive to electrons. So when something's more attractive to electrons, we think of it as effectively more electronegative. What does that do to the energy of its orbitals? Greater electronegativity means what in terms of orbital energy? Lower energy. And so what do you think we can say when it has a negative formal charge? Exactly the opposite. It's less attractive to electrons. It's less electronegative. So the MOs would have higher energy. So now we've described all the factors that will affect energy of MOs in our system. So now it's just time to summarize. Again, I don't necessarily think you need to copy this right now if you're sitting in the room. It's summarizing what we've already said. But maybe leave some space and come back and copy it. We said you split the orbitals into sigma, pi, non-bonding, pi star, and sigma star. Within each category, you order by total electronegativity. Higher electronegativity makes it lower energy. And then the other factors to consider, S character, more S character, meaning SP versus SP2 versus SP3, makes it lower energy. Positive formal charges make it lower energy. Higher negative formal charges make it higher in energy. So when we want to draw an MO diagram, when you're asked to draw an MO diagram, essentially there's 4 steps. First, you draw a complete Lewis structure. The Lewis structure is going to tell you what bonding orbitals you need, what non-bonding orbitals you need, and what antibonding orbitals you need. So you draw your Lewis structure. You make a list of all the molecular orbitals. On the skill builder for this module, these steps are kind of broken out. You'll have some questions that just ask you to make a list of all the MOs. And then arrange them in order from low energy to high energy. And then you put your electrons in. So I'm going to walk through a couple examples. The first example is formaldehyde, CH2O. So go ahead and try going through these steps for CH2O, and then we'll do it together. All right, looking over people's shoulders, it looked like most people had no trouble with the Lewis structure part. Should have carbon double bonded to oxygen. Oxygen has 2 lone pairs. Carbon has single bonds to 2 hydrogens. So then step 2, make a list of all the MOs in the molecule. All right. So what orbitals did you come up with in looking at the Lewis structure? Tongue? All right. Sigma CO. How many of those? 1. All right. Sigma CH. How many of those? 2 sigma CHs. All right. 1 pi CO. All right. Now, every time I come up with a bonding orbital, what do I also need? A corresponding antibonding. So I'm going to need a sigma star CO, 2 sigma star CHs, pi star CO, and the remaining 2 non-bonding orbitals on oxygen, so 2 oxygen lone pairs. All right, so we should have a total of 10 orbitals because we have carbon atom and an oxygen atom, 4 for each of those, and then 1 for each hydrogen. Should be 10 orbitals. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 orbitals. All right, so my orbitals are accounted for. Next, we're going to put them in order from low energy to high energy. So what's going to come lowest in energy? Sigma CO. What's going to come next? Sigma CH. Pi CO. Then non-bonding. Pi star. So yeah. So the question is this how we should indicate the non-bonding? Or you could just say oxygen lone pair if you want. That would be fine. And then at the top we'd have sigma star CH. All right. And then last step is going to be to put the electrons in. Oh, here I'm going to do a little maneuver. All right, so now I'll put my electrons in, and I should have 2, 4, 6, 8, 10, 12 electrons. So 2, 4, 6, 8, 10, 12. All right, everything through my lone pairs is filled in. Antibonding are empty. I'm done. What questions do you have about the process? So the question is this basically what the skill checker is about? Yeah, for the most part. Module 10 basically starts here. There's a little bit more to Module 10. We're going to talk about how we would use this to predict reactions. So I don't know, I may do another example, and then we'll talk about what comes next.